Hey everybody, welcome to Similarity and Diagonalization with me. That is our topic for today. Big idea, why do we care about this, is it lets us recover a matrix A when we're given the eigenvalues and their corresponding eigenvectors, which is pretty darn cool. You can get back to A using just eigenvalues and eigenvectors. So let's dive in to why all the things that we're going to need in order to get there. So first definition, we say two matrices A and B are similar if there is an invertible matrix P such that we can write A in terms of B like this. Quick note, A and B being similar is not the same thing as being row equivalent. They could be, but it does not imply anything about row equivalence at all. So keep those definitions straight. Okay. Next thing, we need similarity so that we can make this statement in this theorem. We've got if A and B are similar matrices, then A and B have the same characteristic polynomial, and as a result, they would have the same eigenvalues with the same multiplicities. So let's go ahead and prove that real fast. So, proof. If we have A and B are similar, we want the same characteristic polynomial. So we're going to start out with the definition of similar. A and B are similar. So that means A equals P, B, P inverse for some P. All right, so we want characteristic polynomial stuff. So characteristic polynomial means the determinant of A minus lambda I, right? That's our characteristic polynomial. So let's go ahead and subtract lambda I from both sides. And while I wouldn't have expected you guys to necessarily be able to do this on your own initially, go ahead and pause here now that I've got you started and see if you can try and manipulate this around by multiplying by the right things. And see if you can get to the end. All right, so we want to eventually get, hopefully, so the same characteristic polynomial means eventually, hopefully, here at the very end of our proof, we will have this, right? So that would be the characteristic polynomial of A. This is the characteristic polynomial of B. Hopefully they're equal. And I just feel like it helps to have this goal in mind. How can I fill this in order to get there? Well, I would like to move this lambda I in with this B. And maybe we can push things around so that we can start factoring out P inverse. But we don't have P inverse with our lambda. So let's go ahead and put P inverse with our lambda. How can we do that? Well, we know that P times P inverse is the identity matrix. So there we go. Now it's in with. So then we can do PB minus lambda P times P inverse. Okay, so we're a little bit closer. If we could factor that P out, that would be really great. Remember, it doesn't matter what side you multiply a constant on. So we're just going to go ahead and put them over there like that. Okay. And then, oh, no, so now we can factor out the p. And there we go. Now we have our b minus lambda I. But we still have that p stuff on the other side. So hopefully that's not going to cause a problem. Sorry, I took a second to rearrange. So now we can say that the determinant of a minus lambda I is going to be equal to the determinant of p times b minus lambda I times p inverse. And then we know things about determinants. It breaks up over products. So determinant p, determinant of b minus lambda I, all times determinant of p inverse. There we go. We know things about the determinant of inverses. Remember, it's 1 over the regular determinant. So we're going to say that's equal to determinant of p, determinant of b minus lambda I times determinant of p. There we go. And then our determinants of p's can cancel out because those are just numbers. So there we go. We did indeed get here. We are now done. Okay. So now that we have that question, if a and b have the same characteristic polynomial, are they similar? Does this theorem work in reverse? Hint, probably not, or else I would have said if and only if in the theorem. But let's see. So here's our question. We are going to look at our eigenvalues for a and b. Let's see. So determinant a minus lambda I is equal to 2 minus lambda, 0, 1, 2 minus lambda. So that's 2 minus lambda minus 0. So lambda equals 2 and then 2 again. Determinant of b minus lambda I equals 2 minus lambda, 2 minus lambda, 0, 0. So then 2 minus lambda times 2 minus lambda minus 0. And then once again we get lambda is 2, 2. Notice here though, same characteristic polynomial. Okay. So we found the eigenvalues, which is what it told us to do, and now it wants us to determine if a and b are similar. Hint, they're not going to be. So in order for them to be similar though, we need to be able to write no, stop being green. A equals p, b, p inverse. Okay, so if they're similar, we can find this p. Want to find p. And I did the tedious calculation. I will go ahead and set it up. So you could say 2, 0, 1, 0 equals, and then we'll just let p be some arbitrary matrix. And then we know that the inverse of a 2 by 2 looks like this. Okay, so you can do it the way that I did it the first time I did it, and you can grind through, and eventually you'll get like, when you multiply this all out, you end up with a 0 in this spot, but the 0 has to equal that 1. And so it doesn't work. But we can be clever. And I'm going to present the clever way. If you want to see it go out the other way, feel free to like grind it out. You can always ask me about it. So we have 2102 is equal to P that we don't know, 2002. P inverse. And so then this is equal to, we can factor out that 2, right? This is P and then 2 times the identity matrix like that. And then we're allowed to shift those constants wherever we would want. So let's shift him somewhere else. But then that's just the identity matrix, so hang on, I'm going to erase it. But then the identity matrix just gives back the stuff we had. So that's 2 times the identity matrix, which is just 2002. It is not the same. So that only worked because B was cute and special and he looked like an identity matrix. But I don't know. I thought it was a little bit more clever and cute than the other way. Yeah, I said cute. But if you want to see the other way, please feel free to ask. Yeah. So hopefully that drives home the point that same characteristic polynomial does not imply similar, but similar does imply same characteristic polynomial. Okay. So, definition. We say that the matrix A is called diagonalizable, which I had to practice saying. That's like a tongue twister for me for some reason. So it's diagonalizable if it is similar to a diagonal matrix D. That means we can write A this way, where D is a diagonal matrix. Let's see. So just a quick note, why this is so cool. It makes computing A to the K. So like if K was a really high power, makes computing A to the K really easy. And I'm not going to tell you why. I'm going to let you discover that on your worksheet. All right. So then next question is, we can do this cool diagonalization stuff, but is there a way to tell that we can do this diagonalization stuff before it's, too late? And yes. So the diagonalization theorem. A matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. And in this case, if it has n linearly independent eigenvectors, we say that P matrix has the columns of the eigenvectors and D has the lambdas on the diagonal. So this is our lazy notation right here. Diag, it just means here are the entries for the diagonal. Assume it's 0 everywhere else. And then be careful though, because like we've got V1 is here in the first column and lambda 1 is here in the first entry. That matters. It doesn't matter so much which one you call V1 and lambda 1, but whichever lambda corresponds to an eigenvector, they have to go in the same spot. So if you say that if you pick an eigenvector to go in the first column, whatever eigenvalue he's associated with has to go in the first entry. You can't just be like, these were the eigenvectors, and then it doesn't matter what order I put my eigenvalues in. Totally matters, totally. And you can see that we're going to do a little bit of a proof here. Just rephrasing this theorem though, A is diagonal if its eigenvectors form a basis for Rn. And we call this an eigenbasis, just for reference. So when A has eigenvectors that span all of Rn, we say it's an eigenbasis. And here is a proof and I'm going to put it in air quotes. It's not a super formal proof. We're going to say A is diagonalizable. Okay, so then that implies A equals P D P inverse. So then what we can write is AP equals, no, other side, PD. Okay, and then if P does equal this guy right here, then we will be able to write the AP using matrix multiplication. Like that. And then same thing with D, except we know that D is just going to be like one entry and then a bunch of zeros. And so it ends up looking like, so V1 times, right, so V1 times lambda 1. And then that continues on. But I don't like that order. We always put constants first, so I'm going to rearrange it. Lambda n Vn. Right. And so then this column and this column of the resulting matrices have to be equal. Right, so this, if we had just thrown our lambdas into our D matrix willy-nilly, we wouldn't end up with this nice V1, which corresponds to lambda 1, V1. We might have gotten somebody else's eigenvalues stuck there. The order matters. So then, let's see. We can say columns of P are linearly independent evects of A, and D equals the diag of lambda 1. And then all these steps pretty much work in reverse. So there we go. Again, air quotes on that proof. That is a little bit of this going on. So he's not a real proof. Okay. So if we wanted to diagonalize a matrix A, here are the steps. You compute the eigenvalues of A. You find linearly independent eigenvectors of A. You construct P and D using eigenvalues and eigenvectors, being careful about the order. Let's go ahead and try this. So we're going to diagonalize a matrix A if possible. So number 1, compute the eigenvalues. So determinant A minus lambda I. That's going to be 2 minus lambda 1, 1, 2, 3 minus lambda 2, 2 minus lambda. Okay, and then that will go ahead. If we do that, we've got 2 minus lambda, and then determinant of what's left over. And then we'll do the next one. Remember, we have to alternate our signs. Plus, minus, plus. Unfortunately, we don't have any zeros to go take advantage of. And then last one. 1 times Okay. And then I'm sure you guys don't want to watch me combine like terms. So this ends up being the result. And I'm sure you don't want to watch me do long division either. And so this is how it factors. So lambda equals 1, 1, 5. Okay. So do you remember when I said you have multiple an eigenvalue show up multiple times? You really ought to try and pick linearly independent eigenvectors. I said that you wouldn't know that until you took another class, like differential equations. Guess what? It does matter, and it matters right now because our theorem said we need n linearly independent eigenvectors. We have two eigenvalues that are the same, and we better be able to pick linearly independent eigenvalues, vectors, for those two eigenvalues. So it was important, and you do get to see it, and I had forgotten about this, and so I'm immensely pleased. So let's go ahead. Step 2. Find linearly independent eigenvectors of A. So if lambda, and this is going to be 1 and 2, is equal to 1, then we get 1, 2, 1, 1, 2, 1, 1, 2, 1, 0, 0, 0. And then obviously row 1 knocks out those guys. Okay, and then we can interpret this if I had more space. So this is going to be V1 equals negative 2V2 minus V3. So then V equals negative 2V2 minus V3, V2, and V3. And then we can break that up parametrically. And then we know, blah, 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 this relates back to null space. We know that they're linearly independent. So then, no, don't do that. I moved extra. Okay. So then we're going to say that, V1 is negative 2, 1, 0. V2 is negative 1, 0, 1. So we have linearly independent eigenvectors for our multiplicity of 2 eigenvalue. It matters, ha ha ha. All right, and then we're going to do lambda equals 5. And we've got this augmented matrix. Negative 3, 2, 1, 1, negative 2, 1, 1, 2, 3, 0, 0, 0. Okay. All right, so I, again, don't think people like sitting and watching me do Gaussian elimination, but here you go. Here are the steps that I use to row reduce. They're not the only option, but here they are to copy down if you would like. So here we go. Here's our reduced row echelon form, which means V1 is going to equal V3, V2 will equal V3, and V3 is free, which means we then get our vector V, which is equal to 1, 1, 1, V3. And then we can get our third eigenvector if we just let this V3 over here, that's not the vector, equal 1. or 300 if you like. Okay, so this is not about eigenvectors. Well, it is about eigenvectors, but we wanted to diagonalize. So then P would equal the columns, which are going to be eigenvectors, which is going to be negative 2, 1, 0, negative 1, 0, 1, 1, 1, 1, which are all linearly independent by construction. D is going to equal our eigenvalues on the diagonal. Notice, see, this is like V1, and this was lambda 1. This over here was V3. This over here is lambda 3. Order matters. Okay, I think I've beat that horse. So then last thing we need is P inverse, which again is a boring process, and so I will just copy it down for you guys. Okay, so then we can write A as the following. Okay, there we go. Technically, this was step 3, labeling it for you guys. Okay. So, there we go. We diagonalized our matrix A, but step 2 isn't always possible. We might not always be able to get those linearly independent eigenvalues that are so important when we have a double eigenvalue. For example, let's check out this. Let's say we've got A is 2, 1, 0, 2. Step number 1, get the eigenvalues. That was supposed to be a 2. So here we go. Once again, that multiplicity problem, more than one of the same eigenvalue. Step 2, get the eigenvectors. So then our augmented matrix is going to be, you go through and you plug in 2 for lambda. So then V1 is free, and V2 equals 0, which means our V vector looks like this. There we go. So then for lambda 1, we can have V1, but then for lambda 2, what do we do for our V2? We can't pick anything that's linearly independent. The only option is multiplying by a number, and linear combinations are not linearly independent. So there is no linearly independent option, which means we cannot diagonalize A. All right, so then the question is, do we have any other tests that maybe work a little bit better. Yeah, we have another one. We have if A is an n by n matrix and it has n distinct eigenvalues, then it is diagonalizable. Really easy proof. You should pause the video and see if you can do it. Oh, I'm not putting air quotes on it. Sorry. This is real proof. So we know we have n distinct eigenvalues. That's what we started with. We want to get to diagonalizable. Remember that n distinct eigenvalues implies n distinct eigenvectors. And then we have a theorem about that. Diagonalizable. Yeah. So literally we just use what we used, or use the theorem that we had like a couple slides ago. All right, so that's it. Yeah, if there was anything that was like confusing in here, let me know. But now with diagonalization, which needed similarity defined, similarity, by the way, was technically 5.2 and not 5.3, but the rest of it was 5.3. Now we have ways to recover our matrix A using eigenvalues and eigenvectors, which is pretty darn cool. But anyway, that's all I've got for you guys right now, and I'll see you all next time.